So now we'll do stuff that will require a small modicum more math than what we had so far. So okay, I've already managed to scare off probably about 10 to 15% of the audience. Somebody just asked me what are their chances that they will get in if they're on the waiting list. Well, I think they've just gone up. But look, don't worry. I mean, the point is you need to know what piece of hardware the algorithms run on before you can design good algorithms. This is why you absolutely must understand the system side as well, at least at a very high level. You don't need to know all the function calls and all that, but at least you need to be able to talk to the engineer and be able to speak the language he or she understands. So that's why it's important that you know a little bit about systems. Okay. By the way, 3 years ago I didn't think so much about systems at all, and you get a lot of respect for those guys once you start working with them. Now, first thing that we're going to do is look at variable and load distribution. So basically the issue is you have a large number of objects, and a priori you don't actually know the ID of those objects. So objects could be users, objects could be movies, objects could be ads that you see, could be customers, products that you sell, whatever. And you have this large pool of machines that happen to be quite faulty rather often. And you want to make sure that you assign the objects to the machines in such a way that each time I see the same thing, it goes to the same machine. So even though I don't know whether you're going to sign up for my new web service, if you do sign up and I decide to put you onto machine number 42, well, you're always going to end up in machine number 42 unless machine number 42 goes up in smoke. Then I want to make sure that you get assigned to some other machine, and always that machine. And if at some point I get too many users, I want to be able to partition the user base in a very graceful manner. And it's actually not quite trivial if you think about it. So the way that can be achieved is through consistent hashing, and I'll show you a little bit on how this is done. And basically, that is one of the keys to building scalable systems, and that not just for the internet, but for any application where you have a lot of data, where eventually the data will get more. So thinking of algorithms design, in the case where you take things to the limit, the number of items that you deal with, has actually turned out to be an extremely fruitful thing. And that not just in the systems area, but for instance, if who of you knows a bit about non-parametric Bayes? Okay, some hands go up, right. So if you think about it, you could do clustering and worry about how you do memory management for a given number of clusters. If you get more memory, then okay, you can handle more clusters. Or you could start thinking in a principled manner, well, what if I had already an infinite number of potential partitions anyway? How do I need to design my algorithm such that it can be implemented with certain guarantees, even in the case of a possibly infinite number of partitions? Now, doing stuff like that will not only, in that case, give you more powerful algorithms and more powerful estimators, but it also turns out that the algorithms, the implementations that you get out of this are very efficient in a realistic small scale too. So taking those limits is a really useful thing. Yeah?
What are these conditions?
Okay, so in clustering, so in clustering, well, you could do clustering into 10 clusters. By the way, thanks for this question. Thanks. I want to have more of those. Thanks. It's really great. Where I could have, 20 or 100 or 200 or maybe 1,000, clusters. Now, at some point, I'm going to start running out of memory if I have too many of those. But I never know beforehand when I see the dot, how many clusters it's going to be. So I could either do some expensive model selection, which scans through the different numbers of clusters, and then have some other machinery sitting on top of it, or you could do the non-parametric based, more modern thing of just taking the limit of, letting the number of possible partitions go to infinity, and then deal with the instantiations of the partitionings in a more systematic manner. And this will actually give you, and we will probably get to some of this much later in the class, some algorithms which can quite well scale to essentially dealing with infinite numbers of objects without having to really worry about the infinity. Or, for instance, support vector machines and kernel methods effectively perform estimation in this Hilbert space, which is typically infinite dimensional, yet you manage to actually pull this off with a finite number of parameters. Now, in terms of scalability for algorithms, what helps to do is to think, well, what if the number of my objects, like users, movies, goods, went to infinity? How would my algorithm break? Which are the problems that I'm going to run into? Or how will my algorithm scale if I give it twice, 4 times, 8 times as many machines? And you just work through the various pieces of your communications pattern, and then an idea that you might be excited about very much, you might realize, well, okay, there's this one term which doesn't look like much, but it actually depends quadratically on the number of machines. Okay, the algorithm sticks. And you do that before you implement. At least ideally you do that before you implement. In reality, well, it's a different story.
Pardon me, so the question was,
yes.
What is the partition? So is the partition...
partition would be a cluster.
Okay, one element of the partition is a cluster, or the cluster is a partition?
Well, the cluster is one cluster is a partition.
Okay.
So this is really just as an example where in essentially non-parametric statistical modeling, you will end up with, in terms of its flavor, a very similar type of questions where the limit to infinity actually improves your actual algorithmic implementation and your understanding of what's going on. But this is really just, okay, I think it's probably a distraction if it's not clear at that point. So we'll see concrete examples of such algorithms as we go through. But by the way, thanks for asking. It's good. More questions. If you don't ask questions, I will start asking you questions. So one thing that I will probably only deal with very briefly are overlay networks. So peer-to-peer, I'll probably just tell you what they do rather than how they work. And the idea there is, and I guess all of us at some point have probably used some peer-to-peer service for research purposes. This is all on record, basically, just to get a bit of an idea on how they actually, in a distributed manner, store objects. This is also because, sometimes people combine algorithms in ways which are very buzzword compatible, but not necessarily very efficient. So you can, for instance, have a peer-to-peer convex optimization algorithm, and it sounds like a very nice headline. Unfortunately, it doesn't actually scale amazingly well. At least I haven't seen a very scalable one where you might really want to do this. The key point is you want to design algorithms in such a way that they are symmetric, so they don't necessarily have a master controller which, if it dies, everything falls over. And they should be scalable such that if you throw more hardware at it, more resources, more harder problems, they will scale linearly. And they should be fault tolerant. So in other words, expect your machines to fail. This is the typical scenario. That doesn't mean that you couldn't actually sometimes write some code which will only run if your algorithm, if none of the machines fails. So this may in some cases be the smart thing to do. Suppose I have one cluster failure in a day. And my algorithm runs in 5 minutes. Should I worry about fault tolerance? Heck no. You should worry about getting that piece of code to run as fast as it possibly can and complete. The probability that it will encounter a failure during its runtime is very low. It's basically 5 minutes divided by 24 by 60, right? Now, if the algorithm should encounter a failure, no big drama, you just run it again. If, on the other hand, your algorithm was going to run for maybe a day or two, and you don't anticipate faults, then your algorithm will never complete. So be mindful of the failures and the types of failure when you design the thing. It doesn't mean that everything that you build must be fault tolerant in the classical sense of it must not fall over if the fault occurs. Okay. Who knows about hash functions? Okay, that's most of us. So for the rest, let me quickly go through this because it's a very important concept. So essentially what the hash function does is like a parametric random number generator. Think of it this way. So you take an object, you feed it into this hash function h, and it maps from the domain of whatever object that you have into an integer in a range between 1 and n. And what the hash function, what you want to do is you want to get the uniform distribution. For instance, if I want to distribute objects over machines, I could take this range here, partition it into intervals corresponding to each machine, and then the machine is assigned based on the interval. This would be a very simple random partitioning scheme. It's not a very smart one, but you could do that. So a naive idea would be each time, the first time I actually see some x, I compute some random number, and then store it in a big lookup table. So next time I see x again, I just do that lookup, and I have all that uniform randomness. So this is perfectly random, especially if I were to actually use a physical random number generator, I would have something very good. But the problem is, this wastes a lot of memory, namely the value in the index as the structure to store things. Now you would think, who in his right mind would be so insane to build something like this? Have you ever done tokenization on text? Who's done that in his? Okay, so you're guilty of that crime. Me too. So basically what you effectively did, well, you didn't quite use random numbers, but basically you built a lookup structure from text to index ID. And in some cases this may be a good thing, but in many cases it's a really bad idea because you don't really care about the numerical ID. And what gets worse is, you start building that tokenization dictionary on one machine, you have the same thing on another machine. As soon as you merge it, well, you will get conflicts and you need to resolve it in non-trivial ways, so you basically can't do it. Much better idea is you use a hash function. Basically, the simplest way would be you set the seed of the random number generator to x, the key, and then you draw one number from the random number generator. So you know probably that if you have your random number generator, you can set the seed of that, right? So that ensures that each time you run the piece of code again, it produces the same outcome. You can set the seed to be anything. As a matter of fact, you could set the seed to be correspond to the bit string of the object that you're putting into it. Then you pull one random number out of it, and okay, that's the poor man's version of a hash function. Now that's really complicated, expensive, and a bad idea for a number of other reasons in terms of implementation. So you just short circuit all that, and you just map from the object to essentially something that's uniformly distributed in the range between 1 and n. Now the merging problem between two machines is a non-issue because, well, I just have the same hash function, so they will always map the same object to the same number onto different machines without the need of any communication. And the lookup speed is independent of how many times I requested things before. Yes?
I was just wondering, is there, you alluded to background problems with this that we're going to talk about later, so I don't want to scoop you, but how do we know that n is always going to be sufficiently large that we're not going to wind up with,
okay, a lot of collisions. Yep. Very good question. So let's do something very, very back of the envelope. So who knows of the birthday paradox? Okay, good. So if you know that, then you already know how to pick in. So basically, the thing is, if I have a range going from 1 to n, then if I draw up to order square root n items from this interval, then the probability of collision, of any collision between a pair, is essentially 0. Whereas if I exceed square root n, then that probability very quickly goes to 1. That's the birthday paradox. Now, in some cases, it may be perfectly acceptable to get collisions. So for some algorithms, we'll actually be okay with getting a few collisions as long as we can bound the detrimental effects of that collision. In some cases, you may not want to tolerate that. So here's an example of when you may not want to tolerate that. So Amazon uses 128-bit for their hash keys. At least that's what they described in their Dynamo paper. And when I read it, I thought, well, 128-bit is an awful lot of bits for a random object. And then you start doing a little bit of the math of, why you might want to pick that number, and you quickly realize that 64-bit would not have been enough. So basically, through birthday paradox, we know that 128-bit key space, so 2 to the 128, means I can effectively distinguish 2 to the 64 different objects. Now, 2 to the 64 different objects is still insanely large, but then you think, okay, how many people are there in the world? Okay, so let's pick like 10 billion. Then we say, well, we want to have the tensor product with all the objects that Amazon might want to sell. And let's say that's maybe 1 billion. Okay, so now we are already talking at about 10 to the 25. And that number gets you very close to 2 to the 64. And so if you want to have a system that can possibly store all user object combinations that you might ever want to encounter, you need 128-bit. This is a very quick back of the envelope calculation. I'm seeing some skeptical faces. Or maybe it's just a shadow. I think it was a shadow. Okay, any other questions about that before I explain a little bit more about hashes? So those perfect hash functions that I alluded to don't really exist in practice. I'm actually going to be fairly reckless in this class, and I'm, unless stated otherwise, going to assume that the hash functions are perfect. So the theoretical computer scientists among you will probably feel rather bad about what I'm doing there. But the point is, it just simplifies the proofs a lot if you can assume that the values hash of x can be treated as random basically as random variables which are uniformly distributed between 1 and n. Now, an n-ways independent hash function is one which you basically cannot distinguish if you evaluate it for hash of x1 through hash of xn from having drawn n random numbers uniformly from that key space. So there's a formal definition for that, and I very much recommend that if you like this, to read up on Uli Maurer's paper about pseudorandom permutation generators. It's a really well written paper. It's not easy reading, but it's extremely well written. So this will also explain to you a little bit on how encryption algorithms work, because basically they generate a pseudo-random permutation. If you think about it, well, what is a code? Well, a code is basically a mapping from one bit string into another bit string, which is sufficiently incoherent that an adversary cannot figure out what the recipe was to map from one string to the other. And a code, by definition, is one that can be inverted, so I need to have the reverse mapping from the encoded sequence back to the original. And there are things like Feistel networks which allow you to design such codes. So I'm not going to go into more details here. Look on Wikipedia for Feistel networks, and you'll see the actual encoding scheme, and it's also in Uli Maurer's paper. For many cases, it turns out, the only thing that you need from your hash function, and that's something that's reasonably easy to guarantee, is two-way independence. So it basically means that the probability that hash of x equals hash of y, so the probability of a collision, is 1 over n for all y's. But the probability of, sorry, this is a typo, so for the scribe first note, this should be h. The probability over all the hash functions that I can draw, the probability of collision for any given pair is 1 over n. Now, in practice, you don't really worry about this so much, and you take things like MD5 or memory hash, and they're actually very, very high performance. So sometimes people ask me, well, which hash function should you use? Just use a fast and reasonably decent one. I can't really see a reason why you should be using anything else but this one. It's the fastest I know. You can be a little bit more reckless, and there's something called a fast linear congruential generator, and your random number generator, for instance, will probably do this. And again, I can refer to Wikipedia for a set of parameters. So for instance, there's a couple of them discussed in Knut's book, but this is actually a better generator. Okay. So essentially what what hashes will allow us to do is to have something that behaves like a sampling device, where we can get random numbers out of it without ever having to store it, and as long as we still recall the key, we can get the same random number out of it. So, for instance, you could think of, getting a Gaussian matrix. Then, well, you could either, invoke your Gaussian random number generator and then actually have to store that big matrix, or you just use each index entry as a seed for the hash function, and then you pipe that into an explicit sampler. And so through that, you would also get, your Gaussian random matrix back without ever having to explicitly store that matrix. So then it's a trade-off between memory and computation. Usually computation wins. Okay, so now let's look at load distribution. This is the first trick. So, and this is something where if you'd had this idea maybe about 12, 13 years ago at Akamai, that's basically how Akamai got started. That and a few other tricks. So let's say I want to make sure that I get a uniform distribution over, over the machine pool. So if I have m machines for any key, the probability that that key ends up at a specific machine should be 1 over the size of the machine pool. Now I'm achieving this by picking among all the machines from the machine pool, the machine for which the hash of the key and the machine ID is the smallest. Since I can assume that hash of key and machine ID is essentially a random number, which one's going to be the smallest is uniformly distributed among all the machines. And it's going to be a different machine for each key. Furthermore, each time I feed in the same key, I will be able to recover the same machine again. Right? So that gives me this uniform distribution. And it's fully determined by this hash function, so I don't really need to explicitly store a table of which key goes to which machine. The hash function is all that I need, and that's a very compact representation. Now, the really cool thing is that if we add or remove a machine, we only have to swap a small number of keys. So, first thing, okay, so let's, how readable or legible is it over here? So, who can, let me draw something and then let's have a vote, and let's see where the vote cuts off at which row.
Switch on the light.
Oh, can I?
So, no,
I think that's what you by the door.
the door.
The left of the door.
No, the
Ah. just pull them all up, but nothing happens. So if anybody knows how to operate those switches,
Let's keep going.
okay, thanks. Okay. I don't know. Okay, good. So let's say these are all of our machines. And I have a particular key X. And I compute the hash of X in the machine ID, and I get some numbers out of it. 2, 4, 9, 1, 6, 3, 5, whatever. So obviously, I'm going to pick this machine here to store the key. Okay. Now, if any other machine dies, let's say this machine dies here, nothing's going to happen, right? So in other words, the probability that I will reassign a key if a machine dies is 1 over n, 1 over number of machines. Because the probability that I'm going to kill the machine that holds the key is exactly 1 over the size of the machine. Okay, so suppose we actually end up killing the machine that holds it. Then I'm going to assign it to this machine here, because that has the second smallest key. Now the probability that that machine has the second smallest key is 1 over n minus 1, right? Because these are uniformly distributed. So therefore, the distribution of keys from this machine to any other machine that I need to do in case this machine dies is also uniform. So this is good, because if I have 1,000 machines and one machine dies, each machine gets 0.1% more load. In other words, I hardly notice it. And it also makes for very nice network traffic. Furthermore, suppose I go and actually add one box. Now, well, the probability that this box, new box here, will have a key value that's smaller than 1, okay, sort of giving it away, I mean, let's say it has 0, right? Then, well, that's, again, 1 over n. So therefore, only with probability 1 over n will I have to move the key from this machine to the new machine, and that will uniformly happen over all the other machines. Okay, question?
I'm just wondering under what would be the motivation for moving the keys to the new machine, or instead of just sort of leaving it empty?
Okay, so if so first of all, when one machine dies, I need to make sure I uniformly reassign the keys, or at least I would like to uniformly reassign it without having to, having a specific master node decide where the data goes. So I want to do that without the need for a central master, because otherwise if the master dies, it takes all the assignments with it. That's just like if the file allocation table in your disk dies, you're done. And that's exactly the thing you want to avoid. Now, it's a very good question, if I add one more machine, why wouldn't I just want to wait until I get more users and then assign? Well, I could actually do that, and this is the traditional way of scaling larger systems. While I get more users, I add more machines, and those new users fill up those new machines. But through that, I'm actually losing quite a bit of fault tolerance, because these systems become more fault tolerant the more machines you add. The probability of losing a particular key will actually go like 1 over number of machines that you have. Well, not quite, because the faults also go up with time. And I'll show you in a moment on how you can deal with the fact that you might lose the machine that has the key. But basically, the really cool thing is you can guarantee that load is uniformly balanced. And you don't need an explicit load balancing algorithm to deal with that. It's basically just in the single line. There's an obviously big downside to that, and I'll show you the next slide on how to address it. But effectively what you're doing is you're designing a uniform distribution over a bunch of objects. So if you ever build sampling algorithms, this is a uniform distribution. Now let's say we want to get a uniform distribution which at any time picks k objects at random. Why would I want to do this? Well, fault tolerance. Let's say, for instance, I have user emails and I want to make sure I never ever lose them, because if I lose the user emails, they will be very upset and I lose a lot of money. Or let's say bank transactions or whatever. So what you do in this case is you assign k replicas. So what you do is you basically take the hash of the key and the machine ID and you pick the k machines with the smallest ID. So in our case over here, we would have picked, say, k equals 3, this machine, and that machine. Now the subsets again are uniformly random over the keys, and each time you pick a new key, well, you will get a different random subset. Again, the same fault tolerance and uniform distribution properties hold. If I add one machine, in this case a fraction of k over the number of keys will move, k over the number of machines, keys will move over. Furthermore, if I lose it, the load will be uniformly rebalanced. Question?
If you lose one, how do you figure out which nodes were stored on there?
Okay, if you lose, good question. So the question was, if I lose a machine, how do I know which data was stored on it? Well, if I don't have any replication, I'm screwed. Data's gone. And in some cases that may be okay, like if I have a cache, then I just have to recompute those things. Now, if I have a file system, this is an awfully bad idea. And actually we'll talk about that in quite a bit more detail later on. But essentially, if I have k replicas, then the other k minus 1 machines can occasionally go through their inventory and ask around, does everybody else also still have this copy? And then, if that other machine is dead, they can decide, oops, okay, actually somebody else should have this copy and reassign. And I don't even need a master to do that anymore. So I could, without loss of generality, make the machine with the smallest ID to be the one who's in charge of that replication for that particular chunk. And if that one dies, I send the signal out to everybody else and tell them, well, all the other machines are dead. Well, this machine is dead. So through that, I can automatically, at a per machine level, deal with replication and make sure that I recover from faults very quickly. Because otherwise, if I have a single master, that single master needs to realize, oops, okay, I've lost all those chunks. Now let me compute a new reassignment policy and send it out to all the other machines and tell them how to transfer the data. And that takes a lot longer than for each machine otherwise. The big Achilles heel of what I just described to you is that this can be really expensive. So if I have 1,000 servers, I need to compute 1,000 hashes. And 1,000 servers is not uncommon. So how can we get around the fact that, well, we still want to have this replication, fault tolerance, balancing and all that, but we don't want to compute 1,000 arguments. So here's one thing that people have suggested. It's called a distributed hash table. You may have heard that from peer-to-peer. So a DHT is actually something very, very simple. You basically take a ring of n keys, make n reasonably large, and you assign the machines to this ring via hashing. So each machine gets a position somewhere here. And then you pick the machine nearest to the key on the left or on the right, doesn't really matter, but on one side. So in other words, if I get an object and I hash it in here, then this will be hashed to the leftmost machine. When I get another object, it's hashed to the leftmost machine, and so on. Now, the good thing is, in this case, my lookup is going to be order log number of machines. Just standard dictionary deployment. That's good. The downside is that if I lose one machine, then all the keys that were stored here have to move over to this machine. So my changes that happen are extremely localized, which is probably not what you want, because this poor machine now will get a lot of more work to do. And furthermore, it gives me a fairly uneven load distribution. Yes, in expectation, each machine gets the same amount of work, but the length of the segment here actually will be quite variable. And I'll show you how variable on the next slide. So how can we fix this? You basically insert each machine more than once. So rather than representing all the resources of one machine by one point on the DHT, you insert it maybe 10, 20 times, maybe only 5 times, and that will make sure that each chunk is now smaller, and so the sum over those chunks is still going to be uneven, but it's going to be a lot more evenly distributed. So let's actually analyze that a little bit more in detail. So the first thing to think about is, well, if we want to know the size of a particular segment, let's say this segment here. Well, without loss of generality, we can pick any machine and we just define the hash of that machine to be 0. Because we can always just rotate the ring and everything around and set this to be 0. So now we basically have n-1 machines that we can randomly assign over that ring. Right? Now, the question is then, which machine is going to come closest to this machine here? Because that determines the length of that segment. So I basically have a random variable x, which tells me the size of the segment, and it's going to be given by the minimum over some other random variables si, which is basically the positions of the other machines. Okay. Now, does anybody know how to deal with minima or maxima of random variables? How to deal with their distribution function? Who's done that before? Okay, that number is a lot smaller. Okay, so let's go through it in a bit more detail. This is a useful trick that we'll see more than once. So, let's take some density, and we can also plot its corresponding distribution function. So, what is, and this is usually called f of x. So f of x is the integral going from -infinity up to x of p of x dx. Right? That's how it's defined. That's the CDF, cumulative distribution function. Now, this of course is also equal to the probability that x prime, which is a random variable drawn from that distribution, is less equal than x. Right? Now, if I have k random variables drawn independently, then the probability that, well, x1 up to xk is less equal than, okay, actually let me call this c to make things a little bit less confusing here, is going to be less equal than c, and since these are all independently drawn random variables, equals the product I going from 1 to k of the probability that xi is less equal than c. Right? Because they're all independent. Can you guys in the back read this? No.
It's very light.
Okay, let me try a different color.
Also on the very right side of the board, it's behind the podium.
Oh, okay. Okay, sorry. So, can everybody read things up to here?
The podium actually moves unless, like, the light something has changed since last semester.
I don't know, but I'm trying to calibrate the screen here. So who can read stuff up? Who can read stuff up to here? Okay. Down here? No. Up here? Okay, good. No, basically I'm just going to make a bounding box. Okay. So stuff up to here is readable. Good. Then I'll just stay in that range. Unfortunately, the equation is outside the range. Okay, let me copy it down again. So the probability that x1 through xk less equal than c equals the product over the probabilities for each individual element 1 to k of xi less equal than c. Right? So far everything's fine. So can you guys not read the stuff down here?
I think they can read their marker.
We thought you were talking about the marker, not
Okay.
the actual physical area
Okay.
that we can see.
I'm talking about, I mean, I cannot do much more about the font than, write with even bolder font, but,
If you could use the black,
okay,
a little larger.
okay, good. I'll try.
But we
So-
can see in that area.
Okay, good. Good. So the point is, since this is the product of these probabilities, and, well, we know what these are, right? They are f of c, basically. Actually, f sub I of c, because they could be differently distributed random variables. So this equals the product I going from 1 to k fi of c. Right? Which is cool. Now, if I have a uniform random variable, what is its cumulative distribution function? It's about the simplest thing you can imagine. So, here's the range, the random variable. So everything below has probability 0. Up here we need to have probability 1 because nothing's going to ever come to the right. And since it's a uniform distribution, the CDF is going to be linear. Okay, good. So now if I have a uniform distribution here, it's going to be, and it's going to be the same distribution, it's going to be, well, C over that range to the n. Or, sorry, k here. And if I have, rather than the maximum, the minimum, I just need to reverse things. I will get 1 minus c to the n. Now, since I have n minus 1 machines that I can randomly assign, or n minus 1, I get 1 minus c to the n minus 1. So in other words, I can explicitly write out what the probability is that my segment length will be greater or equal than c. This is useful. So I have full closed form expression because, of course, I can get the density by just taking the derivative of this quantity, right? We have the cumulative distribution function. Take the derivative, so this is n minus 1 times 1 minus c to the n minus 1. So at least analytically I can, work out the details, and probably somebody actually did that. We're going to take a few shortcuts here and make our life a little bit easier. So the first thing to realize is that the expected segment length is 1 over n. That just follows from symmetry because there's nothing specific about that one segment that I picked. So each of them has the same length. Okay. Now, the only thing that I need to work out now is the probability that a particular segment length will be really long. So I'm going to work that out in multiples of the expected segment length. So the probability that x is going to be greater or equal than k over m, so it's going to be k times larger than its expectation, is nothing else than 1 minus k over m raised to the power of m minus 1. Right? Now, m minus 1 and m are really close, so let's just make that essentially m. Let's take m to infinity, and this works out to be e to the minus k. So in other words, the probability that my segment length is k times larger is bounded by e to the minus k. So I can make that fairly small. Let's say I pick k equals 10, then it basically doesn't happen, but it tells you that still on average you could get segments which are 10 times longer. And you can address that to some extent by simply having a multiple inserts per machine. Okay. So Cassandra, for instance, uses stuff like this, and they tweak things in, let's just say, interesting ways. The last thing in terms of hashing, and if you'd come up with this idea 2 years ago, you would have last year gotten a best paper prize for that. So this is actually, it's actually a very nice paper. It's probably worthwhile reading. It explains things in a lot of detail. It's called SPOCA. I'm not quite sure where they came up with that name, but it's by Chavla et al. Usually it's 2011 best paper prize. And so here's the problem that they addressed. So far, I assume that all the machines that we have are uniformly capable. Now that's of course not the case, because I might have purchased some machines now, and then I purchased some in 6 months down the track, and I have some machines that may be 2 years old, and they all have different capabilities. So there's no point in throwing the old machines away, or to throwing equal amounts of work at the old and new machines. I want to be able to assign the workload such that it's uniformly balanced in terms of their capabilities. So one way how to do this is to basically create an allocation table. Think of it similar to how your hard disk allocates or your file system allocates files on disk. It basically picks a bunch of sectors and it stores the file on it. And now imagine taking a dart and throwing it randomly at the disk. You're going to pick one sector. Now the probability that you're going to pick a particular file will be proportional to the size of the file. Of course, I will also end up with a, so this is like that example here. So here's my allocation table. It's not entirely full, but each block is proportional to the size of the object. In that case, the size of the machine. And now pick, my dart is essentially, hash of the key. And I pick something maybe here. Okay, if I pick that block, fine. Now let's say I pick another location and actually that location is empty. What do I do? Well, I simply throw the dart again. That's effectively what happens. Or you just hash that location, doesn't really matter, it's the same thing. And you keep on doing this until you hit something. So this is really similar to rejection sampling in a sampler if I want to get the distribution where individual probability weights are directly proportional. Well, basically you want to get a sampler where the probability of picking an element is proportional to a given score that you're setting. So, who has done rejection sampling in the before? Okay, good. So this should all look extremely familiar. And essentially the ratio between assigned and unassigned space will give you the rejection rate. So why is it good? It's good because I can do very quick lookups. Again, this is essentially logarithmic lookup from this table. And there are actually interesting tricks if I want to deal with problems where I get some requests for an object very frequently. I just keep on bouncing them off, and I'm not going to talk about that in detail here. But one thing happens is that once you're actually done allocating the entire table, that's it. At this point, you've run out of memory locations and, well, you can't really assign anything else. At this point, you would have to go and maybe double the size of your table, or maybe keep track of which keys you've assigned before. So assign it big enough that you will never have to do that while the system is deployed. And the other thing is, of course, if I get a new machine, I need to actually change this table. But other than that, it's a really good idea. Question? Yeah?
This sounds almost stupid, so why is this such a good idea? Because this empty block is going to be, how large the empty block is going to be how many times, how many times you have to rerun
Yes.
your hash function.
Mhm.
And I mean, it sounds limited and not very
Yeah.
scalable and not
Okay.
distributed, so why
So-
is this great?
So why is it great? It's great because it gives you proportional hashing. So basically where I could have some machines which are 10 times as capable as other machines, I actually can ensure that this machine gets 10 times as many keys. And doing that in a meaningful way is not so easy otherwise. So as a matter of fact, the guys who built Cassandra asked exactly that question, and they went with a variant of this distributed hash table where they assign machines on that ring based on how they think the load goes, and then they get a lot of really interesting scripts on how to do the load rebalancing as you add more machines or remove them. In other words, it actually becomes very much dependent on a human or basically an operator, or at least some other scripts, as opposed to being fully automatic. So this is why it's a great idea if you have a fully automatic system. Now, if somebody can come up with a much more clever proportional hashing algorithm, you should absolutely write a paper about this.
If you have a ring, why don't you just stick as many machines proportional to the string? I mean, maybe the actual.
Well, so what you could do is, that's correct, you could, if the performance can be measured in integer multiples or at least approximated, I could simply hash larger machines more often into the ring. I could do that, but then I also need to make sure I hash machines often enough into the ring to make sure that even if it's a small machine, it doesn't get slammed with a big workload. Remember the e to the minus k dependence on the scaling factor. And so you're starting to get a lot of inserts into that ring. And this would possibly be as well a fairly reasonable way of building a system. Then still at some point you're going to run out of keys. I mean a lot later, because now you're representing probability masses by essentially drawing a discrete distribution. So it's less faulty in terms of scalability, but it will already also give you a fairly expensive algorithm. So I'm not saying this is the only trade-off, but this is actually something where at the moment I don't think people have a really nice and clean solution. So if you have a better solution for that, I mean, you should absolutely publish this. Okay. Any other questions? By the way, thanks for the question. It's good. I really appreciate if you guys ask. So now,
But I
Sorry.
got a question. When you say rehash, when you hit some empty space and you say rehash and hash and tool, when you rehash, I mean, you gotta keep like some kind of a memory of all your functions, because the objects that you already allocated, you use a different hash.
no, so basically there are two ways how you can do it. You can, let's say I didn't hit anything, I just compute another hash. And I just, have a loop, which basically goes like,
You just apply the hash function twice or something?
yeah, well basically, you have I plus plus, I equals 0, hash of x and I in until this happens. Basically, you just keep on computing the hash function with a key and this counter until at some point you get something.
Right.
And in rejection sampling, you would also do that, right? You just keep on sampling until your sampler accepts. And so, of course, there's no guarantee that, I mean, this allows for
I misunderstood the meaning of rehash. So it was like computing a different hash function.
So as a matter of fact, what they advocate in this Walker paper is that once you get to this location, you compute the hash of the location. Because that may be faster to evaluate than hashing the original object. So if this is, some user data, this might be maybe 10 kilobytes. We already hash it into 128-bit vector here. Then hashing that 128-bit vector is faster than hashing this object. And it's just as random. That's the beauty about hashes. Okay, but yeah, that's really just a computational convenience. This paper is very beautifully written. It's very, very gentle in the explanation. Some of you might want to push a fast forward button on it sometimes, but it explains stuff really well. I mean, they deserve the best paper prize for it. So here's something that basically random caching trees. So if you'd had this idea in '99, you would be really rich. So the idea is basically so this was at the time when people started thinking about, building web caches and proxies and so on, and making sure that if a file became very popular, you would actually be able to, ramp up the caching load, and you would be able to distribute the file over more caches and so on, and do that in a decentralized fashion. And of course, if you want to do that without a single master controller, well, you need to build a system that, uses something like, proportional hashing. So what they do is they build random trees. So assume for the moment that I actually know the identity of the object. So I go and build a random tree which starts at the owner of the data. And let's for the moment assume that the objects don't really change. So let's say there's a unique owner of the data. And I build some random tree. And with random I mean I randomly assign machines out of my server farm, out of my caching farm, to those nodes. And so as a request comes in from some requester here, it goes to which maybe by proportional hashing and so on, I assign it to this server sleeve. Now the sleeve will go up the way and check who has a copy of the file. Initially only the root will have the copy of the file. But if the root keeps on getting too many requests, it will say, okay, by the way, from this child we got too many requests, they get a copy. And if then this child gets too many requests, it might say, well, okay, by the way, these two guys get a copy. And then it bounces it further down, and so on and so on. So this ensures that I will get a load distribution which is as balanced as can be for these requests, because it's a different random tree in each case. And furthermore, the depth of the caching level will be proportional, well, the log of the request numbers is going to be proportional to the depth of in that tree up to which I cache. Okay. So this way I can ensure that I get good load balancing, and I don't need to know beforehand how frequently various files are going to be requested. Now, of course, the entire thing gets a little bit more messy as soon as I may have non-stationary request distributions and so on, or where I might have some prior knowledge. Let's say, for instance, I know that this is a Japanese video, then chances are pretty high that I will be serving that a lot in Japan rather than in the United States. So building a completely random object is maybe not such a bright idea, but the gist of it was essentially this random caching tree paper. And I think this is probably one of the more significant papers that were written around that time. It took a long time